Mass spectrometry, or mass spec, is primarily used to determine the molar mass and molecular formula for a particular compound. As we'll see later on, it can also give hints as to the structure of a molecule. Now, mass spec is usually used in combination with other types of spectroscopy, such as IR and NMR, that we'll use later on. It's very rarely used all by itself. Now, the way that mass spec works is we use a mass spec machine and we insert a molecule into the machine. Now, the machine itself uses electron impact to ionize the molecule. The way that the electron impact works is you have your whole molecule, such as this one here, and the machine is going to hit it with a beam of electrons. So this is a high energy beam of electrons. And what's going to happen is they're going to dislodge one electron from a bond in the molecule. So our single electron is here, and that's going to leave the molecule with a positive charge, since we've lost a negative charge, as well as a single electron in the form of a radical. So we're left with a radical cation after this beam of electrons. From here, the machine is capable of reading the particular molecule. If the radical cation remains intact, it is known as the molecular ion or parent ion. This can be symbolized using this symbol here. So the large M stands for the whole molecule. These little symbols, the positive and the radical, are our radical cation. Now, the reason this is known as the parent ion or molecular ion is the mass of this piece is equal to the molecular weight of the entire molecule. Since the only thing that has been lost from this is a single electron, which has minimal mass, the weight is going to be nearly identical to the molecular weight of the compound. So this up here is our radical cation, and its mass would be equal to the molecular weight of the molecule. Now, most often, a radical cation does not remain as a whole structure. Instead, it's going to start to break apart into fragments. Now, with this fragmentation, the radical is going to go to one piece of the molecule, leaving the other piece of the molecule with the positive charge. So what we're doing is taking this radical cation and separating it out into a radical and a cation. Now, after this fragmentation, the only pieces the machine is capable of reading is the positively charged pieces. So this is very important. Mass spec machines only locate the masses of the positively charged particles of a molecule. So these two pieces here, the radical and the carbocation, are the fragments of the whole molecule. So this right here is an example of what a mass spec looks like. We're going to be focusing on the molecule, which is methane. Now on the x-axis here, we have m over z, which stands for the mass of the particle per charge. Now since the charge of the particle is always going to be +1, this is essentially just telling us the masses of the pieces that the machine is reading. On the y-axis, we have the relative abundance, and this is telling us how often those pieces are appearing in the machine. Now, the base peak is known as the tallest peak in the spectrum. So for methane, the base peak is this tall peak right here. Now for methane in particular, the base peak is actually representing the molecular ion, or the mass of the entire molecule. Now, methane is made up of one carbon, which has a mass of approximately 12. We don't need to worry about the decimals after it. And it also has 4 H's, which each have a mass of about 1. So overall, the mass of methane is approximately 16 grams per mole. So you'll notice that the base peak shows up right at the 16 mark. Okay, so this is showing us that our tallest peak, which happens to be the base peak, also corresponds to the mass of the entire molecule. Now, this is a very rare occurrence that the base peak is actually equal to the molecular ion mass. Sometimes the molecular ion peak is not even observed in the spectrum, and that's because some molecules are capable of fragmenting a lot easier than other molecules. And we'll see examples of those in just a second. If we take a closer look at the mass spec for methane, you'll notice that in addition to the base peak that corresponds to the weight of the entire molecule, we also have peaks that have masses less than the weight of the entire molecule. Now, peaks that have a mass less than the molecular ion mass always represent fragments of the molecule. So for instance, if we were to take methane and hit it with that beam of electrons, it would dislodge one of the electrons between the carbon-hydrogen bond. This would form a radical cation, and since we only lost a single electron, it would still have a mass of 16. Now, as we saw previously, this can fragment into both a radical and a cation. So in this case, we can have the H take the radical, leaving the carbon with the positive charge. And again, since the machine only reads the positively charged pieces, we're going to see a mass of 15 representing this fragment, because we've taken the whole molecule and we've now lost an H, which is changing the mass of this fragment to be one less than the mass of the whole molecule. So we see here a peak representing 15, which is representing this particular fragment here. And we'll talk about why some peaks may be larger than others when we get a little bit more into the theory of fragmentation. Now for methane, we can consistently lose hydrogen radicals, which can decrease the mass of this particular fragment. So we can actually end up with fragments where we have masses of 12, which would represent just a carbon, 13, which would be a carbon plus a hydrogen, and 14, which would be a carbon plus 2 hydrogens. Now these peaks show up here. You'll see that they're a lot shorter than the mass for 16 and 15. Similar to methane, in the mass spec for benzene, the molecular ion peak is also the base peak. So let's consider what would happen if we took benzene and hit it with that beam of electrons. Okay, so we have our electron ionization. What we're going to end up doing is we're going to dislodge one of the pi electrons that are located in the aromatic ring. So we'll be left with a radical that is actually stabilized by resonance with these pi electrons in the ring. And then the molecule as a whole, because we lost that negatively charged electron, the molecule as a whole will be positive. Now, since we only lost an electron in this case, we're still going to have a mass equal to 78. Now, this molecule doesn't like to undergo fragmentation, and again, we'll take a look at why something would fragment versus something else in a little bit. But since this does not fragment very well, we're going to end up seeing the base peak exactly at the mass of the entire molecule. So this is our base peak here, and it's also our molecular ion peak. Like most compounds besides benzene and methane, the molecular ion peak for pentane is not the same as the base peak. So pentane is a 5-carbon chain shown here. Now pentane has a molecular weight of 72. So if we take a look over at the peak here for 72, this actually represents the peak for the molecular ion. You'll notice that it's super short. That means that this molecule is going to fragment really easily. This tallest peak here is our base peak. And our base peak represents the most common fragment to form from pentane. Now, if we take a look at pentane, and for all molecules in general, anywhere there's a bond, we can consider it being capable of fragmenting or breaking. So we can consider a fragmentation between 4 carbons and 1 carbon. That could lead to two possible scenarios. We could end up with the 4-carbon chain with the positive charge, plus a methyl group with the radical, or we could end up with the methyl group with the positive charge and the 4-carbon chain with the radical. Now, either one of these is capable of happening. As far as the machine goes, the only thing it's going to recognize is those positively charged fragments. Now let's consider other types of fragmentation. We could break it apart into 3 carbons and 2 carbons. Again, we have two possible scenarios. We could have the 3 carbons with the positive charge, as well as the 2 carbons with the radical, or we can end up with the 2 carbons with the positive charge and the 3 carbons with the radical. Again, the machine would recognize only the positive charges. Now it turns out that this piece here has a mass of 43. And this corresponds to the mass of the base peak, which is also at 43. So this fragment here is the fragment that occurs most readily with this particular molecule and is therefore the most abundant in the mass spectrum. So this is equal to our base peak fragment. Again, we'll talk about the why of this in just a couple of slides. The first step in analyzing a mass spectrum is to identify the molecular ion peak. Not only will it tell you the molar mass of a compound, but if it is odd, it may indicate that the molecule contains an odd number of nitrogen atoms. If it's even, it may indicate that the molecule contains an even number of nitrogen atoms or no nitrogen atoms in a molecule. Now, mass spec is really useful for natural product chemists. These are chemists that go out and isolate organic molecules from plants or sea life or other types of species. What they do is they isolate these molecules and they analyze them for therapeutic effects. So you can test them against cancer cells to see if they kill the cancer cells. If they do, they want to figure out what the structure of the molecule is. And the very first thing they can do is determine what its molar mass is. Then, using other types of spectroscopy, they can eventually elucidate the entire structure of the molecule and begin to explore it as a potential drug. So this is a very useful tool that is used in different types of chemistry. The next thing we can analyze on a mass spectrum is the M+1 peak. The M+1 peak results from the presence of carbon-13 in a sample of the molecule. Now, carbon-13 is an isotope of carbon, and it only makes up 1.1% of carbon atoms. The other approximately 99% of carbon atoms are the isotope of carbon-12. Now, if we take a look at the mass spectrum for methane, we know that the base peak is at 16 and it's equal to the molecular weight of methane. However, this teeny tiny peak up here at 17 represents methane molecules that contain carbon that have the isotope carbon-13. Now, the M+1 peak in methane is about 1% as abundant as the molecular ion peak. And that's because most of the molecules of methane contain carbon-12, whereas only 1% of them contain carbon-13. Now we can compare the M+1 peak to the molecular ion peak to estimate the number of carbons we would expect to find in a molecule. By comparing the heights of the M+1 peak to the molecular ion peak, we can estimate the number of carbons in a molecule. So we'll go ahead and estimate the number of carbons using mass spec data for decane. Now just from the name alone, we know that decane is a 10-carbon hydrocarbon chain. That's because the prefix deca means 10. So we will estimate the number of carbons using this mass spec data and this simple formula. So the number of carbons can be estimated by taking the percent of the M+1 peak relative to the molecular ion peak and divide it by 1.1. This 1.1 comes from the fact that 1.1% of the carbon atoms are carbon-13. So let's go ahead and do this for decane. Now if we take a look at our molecular ion peak, it's almost to 100. We could say it's probably about 98 or 99, but we can just round up and say 100. Now if we look at the M+1 peak, the M+1 peak is about 10 to 12 or 10 to 11% of this molecular ion peak. So we're going to take the percentage of the M+1 peak, which is about 10 to 11, and divide it by 1.1. Now that's going to end up giving us a number of about 9 to 10 carbons. And that proves that we are working with decane, which we know for sure has 10 carbons. Now these numbers are not going to always come out perfectly, so that's why it's important to note that this type of formula allows us to estimate the number of carbons in a molecule. On the next slide, we will propose a molecular formula given data for our molecular ion peak as well as our M+1 peak. In this practice problem, you're asked to propose a molecular formula given the following information. Now, our molecular ion has a mass of 72, so this is going to be equal to the molecular weight of the entire compound. Now, the molecular ion peak is about 38.3% of the base peak. So since the molecular ion is not the base peak, it means that this compound readily fragments. Now the M+1 peak has a relative height of about 1.7% of the base peak. Now we know it's the M+1 peak because it's 1 greater than the molecular weight of the compound. So first, since we're asked to propose a molecular formula, let's focus on the number of carbons. Now the number of carbons formula is we need to take the percent of the M+1 peak relative to the molecular ion peak. And we'll divide that by 1.1. Now the current numbers given are telling us the relative percentages compared to the base peak. So now we need to take these percentages and make them so that we can compare the M+1 to the molecular ion. So first things first, we're going to find the percent of the M+1 peak compared to our molecular ion. So we know that the M+1 peak is 1.7% of the base peak. We also know that the molecular ion is 38.3% of the base peak. By comparing these to one another and multiplying by 100, we will learn that the base peak is approximately 4.4% the height of the molecular ion peak. And this is the number that we want to use when we're estimating the number of carbons. So our second thing is we're going to find the number of carbons. We're going to take our 4.4%, so our relative height of our M+1 peak, and divide by 1.1. And again, this is the percent of carbon-13 atoms in the molecule. This will come out to a nice even number of 4. So we know that we have about 4 carbons in the molecule. Now we know that we have 4 carbons in our molecule, so the third thing we're going to do is trial and error to come up with a molecular formula that makes sense. Now first, let's consider how much those 4 carbons will weigh. So each carbon weighs about 12, And so our carbons in total will be about 48 of our overall mass of the molecule. Now we know from the previous slide that our molecular ion weight is equal to 72. So if we take 72 and subtract 48, we have 24 molecular weight remaining to assign to different types of atoms. Now, since we are dealing with an organic molecule, the most common types of atoms that are going to be in the molecular formula are carbon, hydrogen, nitrogen, and/or oxygen. So let's go ahead and consider different types of molecular formulas. So if we have C4, and then we account for the other 24 of the molecular weight in hydrogens, C4H24, we have to ask ourselves, does this make sense? Can we have a 4-carbon chain that has 24 hydrogens attached to it? The answer is no. So what that means is there could be another type of atom besides carbons and hydrogens. So our next question, could there be a nitrogen? Now with that, we have to consider whether the molecular ion mass is odd or even. If it is even, it means there are 2 or 0 nitrogens in the molecule. If it's odd, it could mean there are 1 nitrogen in the molecule. So since our molecular ion mass is 72, it means that we can either have 0 or 2 nitrogens. Now, if it were 2 nitrogens, each nitrogen is worth 14. So those put together would be would have a mass of 28. Now we only have 24 remaining, so that means we cannot have any nitrogens in the molecule. So our answer to this question is no. So our next question, could there be an oxygen? Sure, an oxygen has a mass of 16. We have 24 molecular weight remaining. So an oxygen can easily account for 16 of that remaining 24. Okay, so now we have 8 remaining. Could we account for the remaining 8 molecular weight in all hydrogens? And the answer is yes. So we could have a molecular formula that is C4H8O. Then the final thing we want to do is we want to verify that this is a possible structure. So on the next slide, we can draw a structure to make sure every atom has the appropriate number of bonds given this number of atoms. So with C4H8O, I'm just going to propose a structure just to verify that a molecule like this could exist. So I will just draw a constitutional isomer with this molecular formula, similar to what we've been doing since the beginning of organic chemistry. So I will put all of my carbons in a row. I'll attach an oxygen, then I'll go ahead and fill in my hydrogens. So I have 8 hydrogens to fill in. I'll go ahead and attach them to the carbons first. And that is all 8 of my hydrogens. Now I want to verify that everything has an octet. This carbon's good, these 3 are good. This one and the oxygen do not have an octet, so I'll go ahead and add a double bond to finalize my molecule. So we do have a structure that could match this molecular formula, and that means that this molecular formula can exist. The presence of an M+2 peak in a mass spectrum can indicate the presence of a halogen such as chlorine or bromine. And that is because chlorine has two abundant isotopes. There's chlorine-35, which is in 76% of chlorine atoms, and chlorine-37, which is in the other 24% of chlorine atoms. Now these two differ by a mass of 2, unlike carbon, which the isotopes differed by a mass of 1. So molecules that contain chlorine often have strong M+2 peaks that are approximately 1/3 the size of a parent ion peak. So for instance, in chlorobenzene, we have our molecular ion peak. Then if we look here, this peak has a mass 2 greater than the molecular ion peak. So this is our M+2 peak. And that's because these molecules all contain chlorine-37, whereas these ones contain chlorine-35. So this is really just pattern recognition. If you get a mass spectrum that has this sort of pattern of an M peak and an M+2 that's about 1/3 the size, it indicates that there's a chlorine in the molecule. Bromine also has two isotopes that differ by a mass of 2. So we have bromine-79, which is about 51% of bromine atoms, and bromine-81, which is the other 49. So it's about 50-50 of these two isotopes. So molecules that contain bromine often have equally strong molecular ion and M+2 peaks. So again, it's just pattern recognition. We have bromobenzene here, and if we take a look at the M and the M+2 peak, they're about the same height. So if you ever see a mass spectrum that has this type of pattern, it can indicate that a bromine is present in the molecule.